Hello class. I wanted to do a little brief introduction to exponential functions and logarithmic functions. We're going to go into just an intro to them, give you an idea, and then if you want to explore a little more, you can explore a little more into both of these. They do have a lot of applications that you can find, so it might be good to explore a little more. First, I want to talk about linear functions, just a reminder of what they look like so that we can see the difference as we start to look at exponential functions. It's a good idea to take notes as we go, so you may want to get some paper out. You can always pause, slow me down. I'm going to use Excel a little bit today too, so you may want to have an Excel document open and ready to go. Alright, so let's look at our linear function just as a refresher. We have y equals 2x. We have our y has an exponent of 1, our x has an exponent of 1. They're isolated here, they're not being multiplied together. So we just have y equals 2x. We could add the plus 0 here to put it into slope-intercept form. So you could see the slope is 2 and the y-intercept is going to be at the point 0, 0, or the origin. But let's make a little table and graph this, and then we'll compare that to what an exponential looks like. So let's make a little table. We have our x values and our y values. And popular ones are -2, -1, 0, 1, 2. Remember, you can pick any point here you want for x when you're working with a linear function. And then we just plug them in to get our y values. So we have equals, our equation is 2 times the x value. Okay, so I have equals 2 times the x value, and we enter 2 times -2 is -4, and then we can just drop that down to get the rest of our table. So if we plot these points, we have -2, -4, and then should be -1, -2. So let's change that. Sorry. Okay, and then we have 0, 0. We have 1 up 2 and 2 up 4. Okay, so we should create a nice straight line with our linear equation. You're increasing at the same rate. We're increasing by 2 each time if we go up by 1 on the ends. Okay, so that was our linear equation, nice straight line. I found a couple points to get us an idea of what that line looked like. Now let's look at what an exponential function looks like. So hopefully you notice the difference when we're looking at an exponential is our x value is now in the exponent position. So exponential gives us that exponent. So that's telling us by looking at this that this is an exponential function. We have the x and the exponent. Again, we can make a little table of value to show us what we're working with. So let's do our x and our y. And we can use the same points for the x if you want. Hopefully I type them in correctly this time. And then let's plug in our equals. This time it's 2 to the power of x. So you can see the difference there. We're using the exponent. And we'll work our way down. Okay, so let's move this over. Make it a little bigger so we can squeeze in these fractions that we're working with here as close as possible. So we have -2 up 0.5, so up a quarter. It's about a quarter. -2 to a half, 0.5. 0 to 1. 1 up to 2, 2 up to 4. Let's go one more just to really get a good view of what's going on here. So 3 up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So you can start to see the curve that we're getting at. This one, our linear equation was nice and straight, but as we connect the dots for our exponential, it's going to, let's see how close we can get to connecting them. And see how fast it's increasing. So you may have heard of exponential growth or exponential decay. So that's what's happening here. Our exponentially increasing. We're working with a 2 to the x here, so it's increasing at a faster rate than just your linear equation. So you can see how we're increasing by a factor of 2. Okay, so that's a little intro to just see the difference between linear and exponential. And let's look at some real-world examples and just work with plugging numbers into exponential functions, maybe creating an exponential function from a word problem. Okay, so we have a word problem that's discussing the worldwide carbon dioxide emissions from 1970 to 2005. And we have a function to deal with. This is function notation f of x. This is similar to using y here. But we're now notating that this is a function. It has the properties of a function. And we're dealing with an x value here to plug in. So whatever we say f of 2, we plug in 2 for x and evaluate. Okay, so it's telling us that x equals 0 corresponds to 1970. So if we plug in 0 for x, f of 0, that will tell us how much carbon dioxide emissions happened in 1970. If we plug in 5, same idea, we get the carbon dioxide emissions for 1975 and so on. So let's look at what we have. We're asked to use this model to approximate emissions in 1970. Okay. So if 0 is 1970, 1975 is 5, so 1980 would be x equals 10. So we're trying to find, we have the equation f of x equals 4, 2, 3, 1 times 1.0174 to the power of x. And we're trying to find f of 10. So all that means is plug 10 in for x and evaluate there. So we have 4,231 times 1.0174, and it's to the power of, we're going to use Excel, so let's plug in the notations we're going to need. So you're going to need your multiplication there. And we have 10. So for our answer, it's going to be f of 10 equals what this gives us when we calculate it. So if we go to Excel, you have equals 4,231 times, parentheses, 1.0174 close our parentheses. We have an exponent, and I like to get in the habit of putting exponents in parentheses, just in case we have an operation or something going up there. It's good to put it in parentheses to be safe. So we have it plugged in, double check that we have all the right values, and we hit enter. So it is giving us 5,027.6, and this is dealing with the carbon dioxide emissions in millions of metric tons. So it's asking for the nearest unit, so we're going to round ours up to one spot, so 5,028. And this again would be the carbon dioxide emissions in millions of metric tons. So this is metric tons, millions of metric tons. Okay, so exponential function has the variable in the exponent, and we're just evaluating it based on the value that we're given. Now let's go ahead and look at our next example and see if we can generate the equation and then use the equation to approximate our answer. Alright, so let's look at our second example, and with this one we're going to have to try to create our exponential function and then use it instead of trying to manually get there for 12 years. So in Phoenix, the average annual rate increase of housing has been 4.2% from the year 2000 to 2019. If you bought a house in 2000 for $125,000, what was the value after 12 years? So let's see what we're working with here. Some of the facts that we know is in 2000 it was 125,000. So I'm going to write that down. In the year 2000 it was 125,000. And this would be year 0. So this is when you initially bought the house. So if we want, it might be helpful if we have our year there. Just so we can use that as we start calculating. Okay, so you have the initial cost in year 2000 was 125,000. We know that it is increasing on an average of 4.2% per year. So in year 2001, that would be 1 year after, we need to find the new price. So if something is increasing by 4.20%, we can use the initial cost times 1 plus the increase, 4.20%. So if you distribute the initial price here times 1, that will give you the original price of the house plus the increase of 4.20%. So that's why we're setting it up like that. If this was a decrease, maybe the houses were decreasing by 4.2% each year, then you would use subtraction here to show the decrease. So let's see what our price value is. And so now we're saying it's just over $130,000. That seems like a reasonable answer as we're moving forward. So let's see what our process in 2002 would be. That would be 2 years after. And again, we know the cost here from last year, and if we know we're increasing by 4.20%, then we can just follow the same process. This times 1 plus the 4.20%. Remember your percent symbol there. And that should give us the increase as we keep moving forward. And again, you're seeing the increase. We're up to 135. So what's happening is what we've done so far is we've taken the 125,000 and I've multiplied it for the first year, so by 1 plus the 4.20%. And that gives me an answer. And then what we did was we took that answer and we just multiplied it again by 1.420%. And that gave us the next year. And then we could, for year 3, we could again take this and multiply 1 plus 4.20%. And that should give us the next value. Hopefully what you see happening here is we're just multiplying each step by this 1.420%. So really what we have in year 3 would be 125,000 times, if we condense these and you multiply things that are the same, you can multiply it and use an exponent. And we have 3 this time. Okay, 1, 2, 3. So this should give us the value after the end of 3 years. So let's go through the long way. And we would have, after year 3, again, we'd take this times the 1 plus 4.20%, and that should give us our next increase. But we're also saying that this should do the same thing. So I'm going to come over here and verify that. Equals 125,000, parentheses, 1 plus 4.20%, and we're going to raise it to an exponent of 3. Try to move it over a little bit for you. Okay, and we're missing the multiplication symbol. There we go. Okay, so we have 125,000 times the 1.420% raised to the 3rd power. And notice the 3 is coming there. And we're hoping that it's going to be the same value as our long process. Okay, and hopefully you can see that we verified that they are the same. So that should lead us into determining a general exponential equation for this to represent any year that we're interested in. So if we write it as function notation, f of x equals, we have 125,000 times our 1 plus the rate. And now the exponent here, we can use x or we could use t since we're talking about years. Whatever you're comfortable with. If I just keep the notation the same we've been using, since we used an x over here, we could use x there. And this would be our equation, our exponential equation to represent this situation, where you have an initial price, it's increasing at a rate each year, and now we are going to find f of 12. So f of 12 should be equals 125,000 times 1 plus 4.20%, and we're going to have it raised, put in our Excel notation, to the power of, and this should give us our value after 12 years. So let's go back to Excel. So we're saying in 2012, which is 12 years after, we should have equals 125,000 times 1 plus 4.20% raised to the power of 12. Make sure we have it typed in correctly. Okay. So we're estimating that it's 204,797 is what we're saying the house will be worth after 12 years. Okay, so hopefully that helps you set up an exponential equation based on a situation and then use it to find a value. As you go through, again, if you're dealing with a decrease, then you would use subtraction here, and the idea is the same. Okay, so exponential decay, you'd be using a subtraction here to get to that point. All right. So again, that was just a little intro to exponential functions. Now we're going to try to tie that into logarithms because they're going to have a nice relationship where you can convert between the two. And sometimes when you start solving equations, it will be better for it to be in an exponential form compared to maybe a logarithmic form. But again, you should be able to convert back and forth depending on which form you have and what form you need. So let's look at what we have here. We have our exponential equation, which is this form, and we want to get it into logarithmic form, which is this form. So I'm going to go through and I'm just going to label the parts. So let's start with our x value is the number that's isolated, doesn't have the exponent. So we have x equals 5. Our a value is the base here, our exponents. A equals 25. And our y value is the exponent, which in this case is a variable, or z. So what I'm going to do is I'm going to take the y equals log base a of x, and I'm going to plug in my values. So the 5 is going to plug in for the x, the 25 for the a, and the z for the y. So we have z equals log base a, we know a is 25, and x is 5. So you notice the base here is lower than the 5. So this is logarithmic form, this is exponential form. So you can go between these two, convert back and forth, and we'll show a little bit later what that does for us as we start to solve those things. Let's see here. So now let's evaluate logarithms using exponential form. So you can use calculators to get some of these, but we're going to try to figure out what they are based on converting them to exponential form. I'm just going to slide this down so we can see it as we work through our next examples. Okay, so we are dealing with log base 6 of 36. So we want to see what this equals. Right now, we don't know what it equals. So we're going to give it a value or a variable. If you look at our form here, y equals log base a of x, we could write that as log base a of x equals y. So that may help you just figure out the variables. You see how the parts are lining up. So really what we're trying to find here is the y value. So let's put it into exponential and see if that helps us. So we have x, which in this case is 36. So I have 36 equals my a value, which is 6, to the power of y. Now, you may be able to identify the answer right away by looking at what exponent, 6 to what exponent will give us 36. But the next step will sort of verify that is we want to turn 36 into 6 to the power of something. And remember, we have 6 to the power of 1 equals 6. 6 squared equals 36, and so on. So we know that 36 is the same as 6 squared, so I can say 6 squared equals 6 to the y. And once you get these values the same, you can just set the exponents equal, and we have 2 equals y. So the solution to log base 6 of 36 is 2. So you're using exponential form to get there. Let's try another one. Again, I'm going to write the log base a of x equals y so that it fits my form. And again, we're trying to find y here. And we're evaluating this log function. So if we convert it to exponential, our x value is the 1 over 8 equals our a value, which is base there of 2 to the power of 1. So again, let's try to convert this into a base of 2 so that we can just set the exponents equal and solve. So if we look at 2 to the first, that equals 2. 2 squared equals 4. 2 cubed equals 8. Okay, that's a good start. So I can say 1 over 2 cubed equals 2 to the y, since we know 8 and 2 cubed are the same. Now, if you have a value in the denominator and you want to move it to the numerator, you're allowed to do that as long as you change the sign on the exponent. So 1 over 2 cubed is the same as 2 to the power of negative 3. And then we can use our rule to say negative 3 equals 1. So the solution to log base 2 of 1/8 is negative 3. So that's evaluating logarithms using the exponential form. We're converting it to one form that we're a little more familiar with, and we can modify it so that we can find our solution for that exponent. Let's keep looking at logarithms. So there's going to be some properties. If you remember working through your exponent rules, you had properties. If you multiply like bases, then you added the exponents. If you divide like bases, then you can take the power of the numerator minus the power of the denominator. So there are different properties of exponents to work with. Well, the properties of logarithms are similar. So let's see what we're working with here. So some key parts that you want to notice is the base. We either expand it or condense it so you can go either direction on this. The bases need to be the same here. And then you're going to take the value x and y, multiply them together if you're working with adding two logarithms. So again, this can go either direction. So sometimes you're going to take a log and break it apart, and this will be more useful to you. And in other times you're going to have it broken apart and you want to condense it. So this is called the product rule. When you're adding two logarithms that have the same base, you can condense it to be the product inside. Quotient, same idea, same base, but this time we're subtracting the two logarithms and we get a quotient or division. Notice that the x from the first value is the numerator and the y is the denominator. That order does matter, so make sure that you're keeping the order. The product rule says that if we have an exponent on the inside, we can slide it to the front or the other way around. So sometimes you're better off with the value on the inside, sometimes you're better off with it as a coefficient. And this is a special property where your value here and your base are the same. And when that happens, we're equal to x. And notice the values in here are the same, and our answer is just x. Because remember that you're working with the value of the b here. They need to be the same. So let's look at a few. If I can bring this down a little bit for us. Okay. So we're filling in the missing values or value to make the equation true. So we want it still to be equal to each other. So notice that we're starting with, on the left side, two logs. They have the same base, that's good, and they're being added together. So again, if we look at our properties, the first product rule is what's going to allow us to take these two logs and condense them down into one. And when we condense it down, notice the x and the y are now being multiplied together. So when I condense this down to just log base 3, it's 7 times 4. Or that just gives us log base 3 of 20. So the missing value that we're looking for here is 28 to make those two equivalent. Okay, and you're just using the properties here. So again, we have two logs. They've been condensed together as just one. There's subtraction. They have the same bases. So we're looking at the quotient rule here. And the quotient rule says that if you have two that are being subtracted with the same base, then the result can just be the log of the same base and the quotient of the two values, or division. So we're missing that value in our problem. So if you look at the result, the y value is the denominator of a condensed version. So this is just 9. Log base 5 of 4 minus log base 5 of 9 equals log base 5 of 4. I think we have one more here. Okay. So here we're dealing with a value in front, 4 times the log base 10 of 2. Now, we haven't talked too much about this or at all, but log base 10 is the base that's assumed. So this could really be written as 4 log 2 equals log of our missing value. Okay, the 10, if it's not written there, is assumed to be there. So either notation here is fine. More likely you're going to see it with the missing 10 than with the 10. So let's see what we're working with here. We have a power happening since we have a coefficient out front. So remember, this r just slides into the exponent of whatever we're working with. So this 4 is going to slide in, and we're going to be left with 2 to the 4th. You could write that as just 16. You multiplied it out. Okay. So that's giving you a little bit of some of the properties that we're working with. Another logarithm that you may run into as you work with them a little bit more is log base e of some value. So log base e can also be written as the natural log. Okay, so if you see the natural log, that just means log base t, if you see that notation as you work through. Okay, and let's use the properties just a little more to try to condense or get a single log out of what we're working with. So we have coefficients on both of ours. We have the same base. That's good. That's one thing you want to check for, is to make sure they're the same base so that you can combine them. If we're going to combine them, hopefully you start to notice that these coefficients can slide into the exponents if needed. This subtraction is leading us to the quotient rule. So we have two different rules happening here. Before you get to the quotient rule, you should move your values up using the power rule. So if we move these up, it's going to give us log base a of 5 cubed minus log base a of 3 to the 4th. So that used the power rule here. That's what we just used. Now if we use the quotient rule, that says that if we have subtraction, we can combine it down to just 1 and make sure that this is going to be our numerator, that's going to be our denominator. So we have log base a of 5/3 over 3/4. And that's getting us to a single logarithm. Again, you can multiply that out if you wanted to. But that's the idea of taking two logarithms and condensing it down to a single logarithm. Okay, the last thing I want to show you is solving a logarithmic equation. Again, you're going to be using some of these properties that we've been talking about. So the idea with this one is you have the x trapped inside here. And maybe we already have it in a single log, so there's just a log here equal to a value. The best idea is turn it into exponential. So if you remember your exponential conversion from back a few slides, we have a to the power of y equals x is what we get to when we use that. So we have a to the power of y equals x. So 5 squared equals 2x plus 4. So I converted it into exponential form, and let's see if that does anything for us. Well, 5 squared is just 25 equals 2x plus 4. Okay, that looks like something we're probably a little more familiar with. Subtract the 4. And we get 21 equals 2x. And divide by 2. And we get 21 over 2 equals x. Our solution for x. So to solve this equation, we actually convert it out of logarithmic form into exponential to try to get to a solution of x. Okay, one last one. Again, we're dealing with an x trapped inside our log, so your best bet is probably going to be try to get it into exponential form. But to get to exponential form, we need it into where we have a log equal to a number. So we look at our two logs. They have the same base. That's a good sign. That means we have our properties that we can use. And if you remember, when we have the addition of two logs with the same base, we can combine those to have the same base, and we just multiply the values on the inside. So x times 2 would just give us 2x equals 3. Okay. And see if you can try to finish this one real quick, and then I'll come back and finish it for you. Okay, so hopefully you converted again to exponential form. 4 cubed equals 2x. 4 times 4 times 4 will give us 64 equals 2x. And then divide by 2. And you get 32 equals x. So that's just a little introduction on exponential and logarithmic equations. They do go hand in hand in working with solving them, expanding them. I hope that was helpful. Have a good day.